So my project is restoring sight, recent progress and future directions in visual neuroprosthetics. And my mentor is Dr. Purohit from Cornell University. So a quick background information and introduction. Around 2.2 billion individuals globally suffer from various vision impairments, including retinal diseases and total blindness. In addition, the growing elderly population may worsen this trend. Some of these visual impairments cannot be fixed by other therapeutic measures such as simple glasses or eye drops. So this leads to the idea of a visual neuroprosthetic. So what is a visual neuroprosthetic? They're devices that are implanted in the visual pathway and can restore sight in visually impaired individuals when electrically stimulated. So I put a picture on the right of what this device looks like, and I'll come back to revisit this diagram in a little. This paper aims to assess the advancements, challenges, and future directions for developing visual neuroprosthetics that restore sight in visually impaired individuals. Just a quick table of contents. There are four major sections to my paper. So first is the methodology. I used a literature review method for this paper because my topic requires a lot of like hands-on work that wouldn't be possible in the scope of the 6 weeks. So I decided to just do an extensive literature review. I used online databases like Google Scholar, PubMed, and ScienceDirect to find both empirical and literature reviews, and I looked at it from both the neuroscience and engineering standpoints to get really the full picture. So first, the neuroscience component, the visual pathway. So just a basic understanding of the visual pathway. So first, light enters the eye through the cornea and then passes through the pupil. And then the lens focuses the light onto the retina, which is in the back of the eyeball. And then photoreceptors, called rosin cones, convert this into electrical signals, and the process is called signal transduction. And then for signal transmission, the optic nerves carry the signals past the optic canal and the optic chiasm to the relay station. So the LGN in the optic tract sends these signals via optic radiations to different brain regions. And the signal is processed in visual cortices, and the brain integrates all of these signals into a full image. Here I put two pictures of how the visual pathway works. As you can see, enters through the eye, passes through a lot of different nerves until it reaches the brain. Okay, and then the different types of visual disorders. Um, a visual disorder is usually caused when a part of the visual pathway is defective. So I put four major categories of visual impairments. The first one being retinal disorders, which is caused by damage to the retina. And there are two main examples, age-related macular degeneration and retinitis pigmentosa. Next, damage to the optic nerve can result in glaucoma or optic neuritis. And then hemianopia, I always butcher this word, but this is caused by damage to the optic tracts and it can result in bitemporal or homonymous. And then cortical disorders are damage to the visual cortex in the brain. So it's actually not in like the pathway, it's rather in the final destination. And that can result in cortical visual impairment and cortical blindness. And here I just put three pictures of these common disorders that I talked about. Okay, the next component is the engineering part of it. So the core engineering principles stays relatively the same. However, each type of visual prosthetic adapts itself to the different um defects in the visual pathway. So when a part of the visual pathway is damaged, the natural transduction process that I talked about earlier is disrupted. So how do we fix this? Visual neuroprosthetics bypass this defective portion by artificially converting visual information into electrical impulses that directly stimulate downstream structures that remain functional. So in other words, they simply skip over the damaged sections and rely on the remaining effective sections for signal transduction. And I put a little picture on the right to show an example of a neuroprosthetic. The system setup is also the same or similar for a lot of the different types of visual prosthetics. So first, a video camera picks up light. As seen in picture A on the left here, the camera is implanted in a pair of glasses that the user wears. And some researchers are working to create an eye tracking design to track like the movement of your head as you move around in your field of vision. However, that is still a work in progress. Next, video processing unit converts the light into signals. So as seen here in the blue device. And then these signals are sent to the circuit wirelessly or with a thin wire, depending on the type of device. And then electrodes on surface of the circuit converts these signals into electrical pulses, which mimics the natural system. And then it can go two ways from here. It can either directly evoke phosphenes in a patient's retinotopic map, or it can just continue with the natural downstream structures of the visual pathway until it reaches the brain, where the brain forms a cohesive visual perception. The system setup is continued here. So how the device converts the light into an actual image that you can see is each electrode, when it's electrically stimulated, it gives off a single phosphene. And what a phosphene is, it's basically like a circle of light that you see. However, it's like a phenomenon because you see like a visual percept, but there's actually no light coming into the eye. So scientists like took advantage of this phenomenon, so they artificially created sight in this way. And as you can see here, each electrode um elicits one phosphene, and each of the phosphene is like a purple square, as seen in this picture. So as you can see, the quality is not that great, which is an area that the scientists are working on. And then the picture on the right gives an example for how the device can be implanted in different areas or different locations of the eye, depending on where the defect is. And here's just an example of the retinal implant, which is a very popular type. As you can see, the device is implanted in the back of the retina so that it doesn't have to go through the retina. It can just bypass that part completely. And there are a lot of different types of prosthetics. So the retinal approach, optic nerve approach, LGN approach, and the cortical approach. And these, if you guys remember, are all key structures of the visual pathway that I previously mentioned. So depending on which part of the pathway is defective, you can just place the implant before that part, so then it bypasses the defective part. And then the materials for the device is also really important. You have to think about the longevity to prevent degradation and decreased effectiveness in the future, the biocompatibility to reduce tissue damage and harm, the flexibility to fit the curve of the eyeball and prevent discomfort, and lastly, the conductivity for supporting ion and electron transport in the circuit. And in the middle, I'm not going to read all that out loud, but I just put a lot of the most popular materials used. Lastly, let's talk about the discussion. First, the current progress. A 2017 statistical survey showed that the number of publications per year in the visual prosthetics field rose from fewer than 50 in the mid-1990s to approximately 400 in 2014. So that's a really big jump in number and popularity. And while the Argus 2 retinal implant was the only FDA-approved prosthetic, numerous prototypes are in various steps in the developmental process. And the production timeline of engineering a visual prosthetic is very lengthy and complex. On the right here, I put a picture of a patient with the Argus 2 retinal implant actually in his brain, so he's currently using that to restore his sight, which is pretty cool. For future directions, there's three main parts or areas that it can improve in. First, the safety. Invasive surgical process may lead to complications during surgery. Degradation of implants may cause tissue harm, and the constant electrical stimulation may lead to electrochemical damage to neurons. Second, the effectiveness. The current visual resolution of these devices is far below the standard. As seen here, it's accessibility. Um, there are a lot of like limitations of who can have the implantation surgery, and even if you can have the surgery, the price tag of 150,000 US dollars for the Argus 2 implant is very unaffordable for a lot of the visually impaired individuals. So a lot of work can go into reducing the cost and increasing the accessibility of these devices. In conclusion, visual neuroprosthetics are revolutionizing the potential for visual restoration. Here are a list of the references I used throughout my research. It's a lot. And I want to give a big thank you to Dr. Brohit and the Talaria team for supporting me this summer. Thank you. A big shout out to Dr. Brohit because he helped me kind of explore this topic because he is an electrical engineer. He understood a lot about circuits, so he helped me a lot when the research papers didn't make any sense. He also taught me how to do research and how to write research papers, so I'm very grateful for that. And I'm very grateful for Talaria for introducing me and giving me the resources to conduct research this summer. So yeah.